Welcome to the content material for Class 17 of Engineering Statics. You should be watching this video before your 17th class. In this lesson, we will learn what is a frame and how it's different from a truss, how to determine the forces in members of a frame, and how to deal with distributed loads. In our last two classes, we have looked at trusses. One of the key assumptions of a truss is that the external forces are applied at the joints. That allows us to consider each member in a truss to be a two-force member. A frame is different from a truss because the forces can be applied anywhere on a member. Sometimes those forces are distributed loads. They are spread out over an area. Therefore, we have multi-force members in a frame. And as such, we cannot use the methods that we used for trusses. Today, we will learn how to solve for the forces in frames and how to simplify distributed loads. So, let's look at this simple frame. It's a frame because we apply a force here and a moment here, and not at the joints. When solving for frames, we first separate the frame into separate members. We isolate each part. In this example, we see two members. So we will separate into two parts. Then, on each part, we will identify what forces are acting on that part. If we identify a two-force member, be sure to label those forces as acting equal and collinear to each other. This example does not have any two-force members. Finally, the forces acting between two parts, such as at this pin, where the two members are connected, we have to label the forces as equal and opposite. So these two members connect at the point B, so we know that the forces Bx and By are equal and opposite across these two members. Let's look at an example of how to solve for a frame. In our first example, we see that we have a two-member frame with a force applied in the middle of member BC. So we're going to start by separating this frame into its two parts. So I'll draw each member. I'll draw member AB and member BC separately. And then I'll identify the forces that are applied to it. Now the first thing we can do is recognize that member AB is a two-force member. And because it's a two-force member, we know the direction of the force. And I'll call that force AB. And we can put the opposite and equal force reaction at pin B onto member BC. We'll add our external force. I'll call that F1, which is equal to the 2,000 newtons. And there's some reaction at the pin C. Now, if you don't recognize that member AB is a two-force member, that's okay. It will just take more work to solve. So let's go on, and we're asked to find the reaction at pin C. So we can look at member BC. And the first thing we can do is we can find the sum of the moments about the point C, because that allows us to solve for the force AB. So the first thing I see is that the force AB creates a negative moment, but it's only the y component of that that'll create a moment about the point C, and it's a distance of 4 meters away. There's also a positive moment from the 2,000 Newton force, and that's at a distance of 2 meters from the point C. And so I'm able to solve for the force AB. We find that's equal to 1,154.7 newtons. Now, moving on, we can solve for the forces in the x direction. We see that that's equal to 577.4 newtons. And so we have the x component of the reaction at C. And if we sum the forces in the y direction, we can get the last component of that. So we have the y component of AB. We find that Cy is equal to 1,000 newtons. So we see that the x component of the reaction is pointing to the left, and the y component is pointing up. The next topic we need to talk about is distributed loads. A distributed load is a load spread over an area and is not applied at a single point. For example, in structures, the weight of snow on a roof or the weight of cars on a parking deck are considered distributed loads. When we analyze structures subjected to distributed loads, we have to simplify those distributed loads into equivalent concentrated forces first. In this class, we will consider 4 possible shapes for distributed loads. The simplest is a uniformly distributed load. The weight is equal across the entire area, and we draw it like this. A uniformly distributed load is converted to a point force by taking the area of the rectangle. So, the weight W times the length L. And that point force is located in the middle at L over 2 from the edge. The second shape of a distributed load is a triangular distributed load. Here, the weight increases from 0 on one side to a maximum of Wm on the other side. To convert this type of distributed load to a point force, we take the area again, and this time the area of a triangle. So the area is the maximum weight, Wm, times 1/2 the length. And it's located 1/3 of the length from the maximum edge. The third shape is a trapezoidal load. And actually a trapezoidal load can be broken into a rectangle and a triangle on top. Or we can use this formula, which shows us that we can find the length or the location of that point force and its magnitude. And finally, the fourth shape that we'll consider is a hat shape. Again, this could also be considered as 2 triangles. However, we can also use this formula, which shows us that the maximum height is the same as a triangle, so 1/2 the maximum height times the length, and it's located in the middle. Now there are other shapes, but we won't be considering them in this course. So let's look at an example of solving a frame that has a distributed load. In this example, we again have a frame, and this time A and C are both pins, and we're asked to find the reaction at those pins. And we also see that we have a distributed load. So as usual, we'll start by separating this frame into its 2 parts. So we have the reactions at those pins, C and A. And the other thing we have is the reaction at B. which will be equal and opposite to each other. And the last thing we have to do is we have to change that distributed load into a point load. So on each member, we see that there's a uniform distribution. So it's going to be equal to 400 newtons per meter times the length, which is 1.5 meters on each one. So we know that this is equivalent to 600 newtons of force at the middle, and so that's a distance of 0.75 meters from the corner. Before we can do that, though, we need to consider the entire frame. So if we draw the entire frame, we know that there are the reactions at each pin, and overall there's an external force equivalent to 1200 newtons, which is the result of the distributed load, and it's applied directly in the middle of the distributed load. And we also have this 600 Newton force over here, which I forgot to draw on this member here. So if we look at the frame overall, we know that we can take the sum of the moments about the point A. So if we take the sum of the moments about the point A, then we're able to solve for Cy, because Cx, Ax, and Ay all go through that point. So doing that, we can find a positive moment from the force Cy, and we have a negative moment from the distributed load, and a negative moment from the external force. And so when we solve for Cy, we find that Cy is equal to 1,200 newtons. Moving on to summing the forces in Y. We find that AY is actually equal to 0. And we can then move on to the forces in the x direction. Here we're unable to solve directly, but we know that Cx minus Ax equals 600 newtons. So we can move on to just one of the members. So finally, if we look at just member AB, so I'll go back and I'll draw member AB again. Again, we see this 600 Newton external force. We have half of the distributed load, which is 600 newtons in the middle. We have the reaction at pin B, and we have the external forces, or the reactions at pin A for AX and AY. And so if we do the moment about point B, we can ignore those forces. We can ignore the reaction at pin B, since we only want to solve for the reaction at pin A. And so when we set up that equation, we find so here we see that AX is negative. In other words, it's opposite to the direction we drew it. So in fact, AX is actually pointing to the left. And we can go back to the equation with Cx and find that Cx is equal to 450 newtons. So ultimately, we've now solved for the reactions at the two pins. So we know that AX and AX is pointing at a magnitude of 150 newtons to the left. AY is 0. CX is 450 newtons, also to the left, while CY is 1,200 newtons, pointing upward. So we see that when solving for frames, we often need to also consider the entire frame as a single rigid body, and we also need to consider individual members in order to solve for what we're looking for. And so that's it.